Hello friends, good morning. Myself prof.a.k.chaubey. I am again here to discuss an important topic of physics under physics made simplest. My topic today, as last time we have completed the alpha decay, gamma theory alpha decay. Now I will be talking about beta decay, another important phenomenon of radioactive decay. You know, I am making this YouTube videos so that these may be used by the interested students in future. I have about 59 years of teaching and research experience, and now I want to use my remaining lifetime for making videos which may be useful for the students. I am making two types of videos, astrology and also physics. Astrology under the heading Ganpati Avad Astrology, and physics is made simplest for physics students. So this is, astrology is my hobby and physics is my passion. I love teaching, so throughout the life I have been teaching all branches of physics. And now I am 80, I want to continue to be active in physics because I can't leave physics. So this is the series of my physics videos, physics made simplest, to help you, my dear students. Okay? So my topic today is beta decay. I have completed alpha decay. So what is the beta decay? We observe in the nature many elements continuously emitting beta particle. Now it is experimentally known as that beta particle is nothing else but beta particle is very similar as electron, means its mass, charge, spin, all the properties of beta are similar to electron. So it means they are coming from the element atom, means they are coming out from the atom. Okay, coming out from atom freely in nature. That means without providing any force. Whatever coming out from atom in nature freely is natural phenomena. So this is natural phenomena, and when we provide some energy, we give some force, that becomes man-made phenomena, means that comes under the nuclear reaction. So nuclear reactions, particles are emitted when we bombard some projectile on the element, on the atom, so that energy is given and system changes. So that is the aided system, means if we provide aid from external agency. So providing energy from outside becomes nuclear reaction. But this coming out of any radiation from any element in nature is natural phenomena. So beta particles which are similar to electron are readily coming from an element, atom. Why it is coming? From where it is coming? From where it is coming? The question is that whether, now I pose a question to you, think on this for a moment and answer that why, whether beta emission is atomic or nuclear. Process. Whether beta emission is atomic or nuclear process, whether the electrons are coming out from atom or whether they are coming from nucleus, what is happening. So beta, but we know, before discussing this, we know that what is actually beta process. We have two types of beta. We have two types of beta activity. Means beta negative, that is electron, and beta positive, that is anti-electron, or that is called positron. So these two processes, emission of beta negative and beta plus, and another process is which comes under this. These are weak processes, and weak process, another process which is called electron capture. Electron capture or EC. This also comes under the heading of weak interactions. So that is these three processes: beta minus emission, beta plus emission, and electron capture. These are the three weak processes. So we want to see first whether the beta emission is atomic or nuclear process. What to do? I have arguments, or you suggest me the arguments. You can mail me or you can discuss with the comment. You can give your comments. One is beta electrons in atom are not free. These are bound. These are bound electrons. Some energy is required. Some energy is to be supplied. For their emission. What the meaning is that electrons in atom are not free. They are bound in atomic shell, Bohr's theory. They have some Coulomb force and revolving on some orbit. So to make them free, you have to pump energy from outside. You supply energy. Means you have to hit by some projectile with energy so that electron gets energy and it's emitted from atomic shell, like photoelectric effect. So electrons in atom are not free. If they are not free, they cannot come in the nature without any external help. You want to make them out, you have to give energy. But beta decay is a natural phenomena in which no external force is applied, it is automatic. So these electrons in atom are bound, so they cannot be coming out freely. It means that beta activity, radioactivity is not an atomic phenomenon. These are not atomic electrons. One reason, because they are not free. So they are not atomic electrons. The second reason, beta decay has beta minus electron and beta plus positron emission. Beta decay has beta minus emission, electron emission, and also positron coming out. But positron doesn't exist inside atom. So from where then positron is coming? This positron, how this positron? From where? Positron is so from where? Positron doesn't exist in atom. From where beta plus is coming? So remember, as beta plus is not there, so how it is that beta decay, some elements are emitting beta negative, electron-like particle, some elements are emitting positive anti-electron, that is the positron. So how it is? It is not so easy. How to produce, how it is has been produced inside atom. It means that the beta emission is not an atomic process. If atomic process, then how positron is coming? What else? What else argument you can give? Or you can get any some new argument, you can tell me in the comments so that I will rectify, modify my idea. Number 3, when betas or when electron emitted from atom to vacancy is created, which is filled by higher shell, electron difference of energy of two shells emitted as photon, energy h nu, or X-ray. When beta particle is, when electron is coming out from atomic shell, higher electron should fill the vacancy because these are atomic shells. If suppose this electron is going out, this vacancy created, this electron will come out, jump, and this radiation H nu is emitted. Difference of the two energies or shells, difference of the energy of two shells is emitted as radiation, photon or X-ray, depending upon the atom. In lead, it is 80 kV X-ray. So the energy of this radiation may be few kV. So whenever electron is emitted, there is associated photon. Photon must be emitted, but beta emission has no associated photon. Beta emission has no associated X-ray or photon, no radiation. Maybe some gamma wave coming, that is something else. But beta particles, when electrons are coming out, there is almost every time some radiations like visible photon, ultraviolet photon, infrared, red photon, or maybe X-rays are emitted. But in beta decay we observe many pure beta emissions also. So where is the associated radiation? It means this phenomena cannot be atomic, and hence beta decay is not an atomic phenomenon. It is a phenomena taking place from somewhere else and not the atomic phenomena. So I am sure now you follow that beta particles are not coming from atom. Any other remark? Yes, there can be one more remark on that. Also there can be one more remark. What is that? Emitted electrons from atom have discrete kinetic energy. But it is not so with beta. Beta are not having discrete energy like gamma ray. No, beta have. So betas have continuous energy starting from a minimum which is nearly zero up to a maximum. All energies are coming continuously, not discrete energy. And hence beta particles are not coming from atom. Okay? So this picture makes very clear in your mind that though they are coming from element, atom, but they are not coming from actually from atom. Beta particles are coming. This is beta decay. Is weak decay. Means no strong forces, no strong nuclear forces are involved. Beta decay is weak decay, no strong nuclear forces are involved. So weak decay, slow process. Well, when beta decay is not atomic phenomena, then how they are coming? So these are means, though these are not present, in nucleus, but these are produced inside. So these are produced inside the nucleus. How it is happening? How beta decay is coming out? Well, just because they are not in the atom, so they are coming. From where they are coming? They are coming out from atom. So it means no atomic electron, then it must be coming from nucleus. But they are not present in the nucleus. Then how they are coming? The process is that beta minus decay, we have a nucleus X having atomic number Z, mass, atomic mass A, is decaying to the beta minus, and remaining daughter product and residual nucleus is Z plus 1 charge, Y and atomic mass same, plus a beta particle, that means electron type, it is a minus charge and 0. This is written also beta negative or minus C, plus energy. So a parent nucleus changes to another daughter nucleus, its charge increases by 1 unit, then a negative particle, so the charge conserved is emitted with some energy. So this is beta minus process. In nucleus it is produced at the time of emission, means at the time of emission one of the nucleus changes like that. Or this can be written because this is charge increasing, means mass remaining same. Charge increasing means one neutron converted to proton. This phenomena can also be written as a neutron of 0 charge, 1 unit mass, gets converted into 1 unit positive charge proton of 1 unit mass, and then we have electron of minus 1 charge and 0 mass plus E plus 2 energy, that 2 beta minus. So in this neutron converted into proton and electron emitted with some kinetic energy. So this is now beta minus process, as we know, and the other beta plus decay is written as that parent nucleus gets converted into a new system Y, mass remains same, but if Z changes by, it is plus 1, it becomes minus 1. And emitted particle is plus 1 charge, and like positron, we write this also as beta plus or 2 beta plus. This phenomena in which parent nucleus gets converted into a new daughter nucleus with charge less by 1 unit, and a positive electron is emitted, that is called positron. Mass is nearly 0 as compared to mass of the nucleus. So, and this energy available, 2 beta. The third phenomenon which also comes under weak interaction is EC, that is electron capture. That phenomenon is that electron is captured by a proton. Electron in the atomic shell, which is very closest to nucleus, gets captured by a proton of nucleus, and the proton captures this, it becomes neutral, means this is Zxa plus 1 electron, so this has become charge decreases by 1 unit, Z minus 1 Ya. Energy in terms of some radiation. So this phenomena, capture of, means a proton captures an electron to get converted into neutron plus energy. So this phenomena is proton plus electron, electron capture EC. All these three phenomena comes under the weak interaction, and that is called beta reductivity. this phenomena is as beta decay. Now what we have experimentally, we have observed what are the experimental observations which we see. See, experimental observations. What people have observed. Just like the Geiger-Newton relations or Geiger-Newton diagram in alpha decay, we have here one experimental observation which is we plot like here. Log of lambda, that is the decay constant, and on this side, log of energy and log of lambda on this side. We get a straight line like this, and almost all the beta elements are lying on this, like this. Some have lines like this also, means some nuclei have like this also. These are called Sargent diagram. Sargent got these diagrams after doing experiment, after measuring the lifetime and calculated decay constant and energy of the beta. He found that almost all the nuclei are lying on one straight line, but there are few on another straight line, and this has got high energy and low decay probability. Means these are having low energy as compared to them, and low energy and like this lambda is also high, but I have a smaller half-life. These are large lifetimes. And large energy. Energy is high, beta particles. This energy is small and decay constant very large. Decay constant large means smaller lifetime. These have large lifetime and large energy. So these are two types of separate lines. Later on these were called forbidden transitions. Forbidden. What the forbidden, I will explain later on. And these are allowed. Allowed transitions and forbidden. Those have got high lifetime or decay probability is less, and the same energy here low. Large energies we have some decay probability. So these are called forbidden, these are called allowed. These two types of transitions were classified later on. But we have Sargent diagram. So a theoretician has to explain this type of phenomena. Just like in alpha decay, we have explained the Geiger-Newton relations theoretically by Gamow theory. Here also, we have to develop some theory to explain the Sargent diagram. So these are the experimental observations. And what else experimental observation is? Number 2 is energy spectrum. While energy spectrum is energies of beta particles emitted from any nucleus or different nuclei, they are measured and experiment is done and energy is plotted, say E beta plotted on, and this I know intensity. So intensity and E beta, it is found that the graph is of this type, where this meets, this was called EM or E end point energy or maximum energy. What is observed? That beta spectrum is not discrete, as I told you in the beginning. Betas are coming all different energy, means continuous. Maximum energy is EM, and this is the all betas of energy are coming. So this we have to explain. The Sargent diagram and also the why or how the beta spectrum is continuous, this we have to explain. So this I will try to explain. I will explain the reason of this, I will explain the reason of this. We will develop, we will write results of Fermi theory from beta decay, from Fermi theory, I will explain this. But let us write the beta equations, the energetics of beta decay. If we write, say, what the energetics of beta decay are, say, energetics of beta decay, negative beta, negative beta. So how now we represent negative beta decay? Any beta decay, how we represent that? By equation. Well, a parent nucleus, or we write mass equation. We write mass energy equation for beta decay, that a parent nucleus of charge Z, nuclear mass say, or we write nuclear mass Mn of Z and A. This is the nuclear mass. This is decay. Or first I give you elementary thing that, that possible, that mass Mn, nuclear mass is M, atomic mass. Then we write phenomena Zxa is Z plus 1 Ya plus beta minus, or that is minus E like this, plus Q beta. This is written in terms of mass energy equation, that this mass is converted to this thing. So we write that nuclear mass of Z and A is equal to this mass, nuclear mass of Z plus 1 and A plus mass of electron plus Q beta. This is the mass equation. Well, this you can write by multiply by C square, you will have energy. So this we can write that Q beta minus is M Z A minus M N Z plus 1 A minus mass of the electron. This goes to this side, this side. C square, energy unit. Energy unit. This is mass unit. Mass converted to multiplying by c square. E is equal to mc square, Einstein's energy mass equation. So this mass, q beta was here in mass unit, now it is an energy unit. So this must be, this is nuclear mass. Now we remove, I change this nuclear mass into atomic mass. How we get nuclear mass from atomic mass? Well, from an atom you remove all the electrons, neglect the binding energy because some energy is spent to remove. So that is what I am omitting that. So from atom we remove all the electrons, we get nuclear mass. So how we get nuclear mass? Nuclear mass we get from atomic mass m of Z A, removing Z electron, neglecting binding energy, minus m A Z plus 1 and A and minus will be plus, so plus Z plus 1 and ME minus ME and C square. This is now q beta minus. So q beta minus is given by this expression. What does it mean? Q beta negative, well this can be a minus ZME, this is plus ZME, and this is minus ZME. So minus ZME plus Z plus 1. So 1 ME is cancelled here and this plus Z minus Z, this cancels here. So what we get? Q beta minus is M mass of the Z A and minus mass of the Z plus 1 and this A and in the units of C square. But q beta is more than 0 for beta decay. If beta decay to take place, q beta should be more than 0, means some energy must be there. Otherwise beta particle will not come out. So beta should have some energy, means this thing must be positive. So for beta decay, we have that this thing must be more than, so MZA must be more than MZ plus 1. This is the energetics or condition for beta decay. We call energetics of beta decay. Means q beta must be positive, so this thing must be more. Beta decay to happen, the parent nucleus mass must be more than this. Other way it will not take place. It will not, that this way the heavy time is like it. No. So this is the limitation, or you can say energetics or the condition for beta minus decay. Similarly we can have condition for beta plus decay. What is that? Beta plus. We can write that Z of XA is Z minus 1 by A and beta plus, that is electron, 0 mass, plus q beta plus. Or we can write that what is happening? A proton here is converted into neutron. Remember, free neutron, as neutron mass is more than proton, can decay to proton. And the energetics possible, because energy of mass, neutron is more than proton. But free proton cannot decay into neutron, because free proton mass is less than neutron. But bound means inside the nucleus, it gets the energy from surrounding, from other nucleons, from the nucleus. So that energy mass of the proton becomes more than neutron. And the bound proton inside nucleus can decay into neutron. But free proton cannot decay, because mass is less. So this is happening, that proton is decaying into a neutron and beta plus and Q beta. Let's start. This is inside the nucleus, but not outside. If outside free proton can decay, then how the system will be stable? How any element chemically can exist? Because these are bound systems. They are, as I told you for decay, that nucleons are bound by binding energy per nucleon around 7-8 MeV. So this is possible. We can write the Q beta equation and energetics of this as in terms of masses, that nuclear mass of Z and A is converted into nuclear mass of Z minus 1 and A, and this is plus mass of the electron, that is one electron is going out, plus Q beta positive. So this means in the energy, or you convert into atomic masses, and then you write the energy units also. You can write that M Z A M N or M Z A on this side. How M Z A? Minus. This will be, you have to subtract, remove the electron. How many electrons? Z electron. This is M N atomic mass Z minus 1A, and remove from this Z minus 1 electrons plus Me plus Q beta plus. So what you get here? You get here that MZA, so that is minus ZME. This is minus Z minus 1 Me plus Me. So minus Z Me and plus ZME, so plus, this becomes MZA minus MZ minus 1A, and here twice this minus, this comes this side, minus twice, minus ZME this side, and that side minus ZME cancel. Then minus Me and plus Me, so this becomes minus 2Me. This thing is equal to Q beta plus. So Q beta plus is equal to, in units of energy, C square. Energy units, Q beta is MZA minus MZ minus 1A minus 2ME. So what we get? For positive beta decay, we get for beta positive emission, Q beta must be more than 0, and this gives us M ZA must be more than M Z minus 1A and minus 2ME. Oh, this is plus, because when this we write on that side, this must be more than this means plus. This minus this. This must be more than this. So what we get? This condition that mass of parent must be more than this mass plus 2ME electron in energy unit. So this is the condition for beta positive decay. And for EC, electron capture, what we get? EC, that means the Z, X, A captures a atomic electron and it becomes Z minus 1 A plus Q of E. This is so simple that this mass, nuclear mass, and this you can convert atomic mass. So you can write simply that mass of Z and A must be more than mass of Z minus 1A. That Q is more than 0. This condition must be fulfilled. So electron capture is the process in which this electron sitting in the, and this is the nucleus. So, and this is proton and neutron. So this proton captures, because it is very close. This electron is captured by the proton. So that is called electron capture. This happens, means we get this thing in some energy after that, QEC. So all these phenomena are weak interaction. They come under the weak interaction. Now what we get? So beta. Now we are talking about the conservation laws of beta decay. What conservation laws are observed or obeyed in beta decay? In general, the same conservation laws which are obeyed in any interaction. So here also we have conservation of, say, conservation of energy mass. When we write the equation of conservation of energy mass, what is the conservation of energy mass? That mass energy is conserved. So we write the energy of the beta particle and we see energy of beta particle and what the energy Q beta minus, that is the difference, means energy of beta, that Q beta we know is available, is what Q beta. We write the mass of A minus mass of Z plus 1 A. This C square. This is the Q beta. This Q beta is gone, this is given to the, this energy is taken by beta particle, energy of E beta. This is this total. But what we observe? We observe that this total energy, this thing is E beta, we write, this is equal to, say, EM plus something. That is when, or this is the maximum actually, E beta, that is the maximum mass. This is the mass difference is EM maximum. But we find that E beta is equal to maximum and from 0 to maximum. So that is E beta is equal to, say, suppose E beta or total energy EM is equal to, say, maximum energy equal to, say, E beta plus something more. Because if it is EM is equal to E beta maximum, then good. But E beta can be any value from a minimum to maximum, that is EM. So maximum EM, this maximum EM is E beta suppose, then EM is, so E beta can be any value. starting from E beta is any value starting from. So where is going this? Or where this remaining energy? Remaining energy. It means if E beta, this is Em, so if E beta is this value, this is the E beta, then what is happening to Em minus E beta? Where this is going? Because energy is conserved. Energy conserved means this maximum energy Em or this thing. This must be equal to the energy. But energy beta is say this or this or say this. Then E beta plus something more does become Em. So where the difference of Em minus E beta is going? Where this difference is going? So Em should be E beta plus this energy. But this energy E beta can be any value from here to here. So where the difference of Em minus E beta? If E beta is Em, only then conservation of energy. Since Em minus E beta is some positive number, if both are equal then difference is zero, no problem. But if this difference E beta has any value here to here to here to here, then where is the remaining energy going? Em minus E beta. So what does it mean? We don't know where Em minus E beta is going. Energy conservation only. Energy conservation only when E beta is equal to Em. If all particles have this E beta equal to Em. But in E beta prime, E beta double prime, E beta etc., these betas energy, then where this E beta Em minus for beta energy E beta prime or E beta double prime, where the difference Em minus E beta prime. Where this? So energy is not conserved because Em is E beta prime plus something here, that is Em minus E beta prime. So where this energy is going? So energy conservation law is not valid. It appears that energy mass is not conserved. In beta decay, but it is not possible. In any interaction, energy mass is always conserved. So how it is happening that this energy conservation law is not obeyed in this beta decay? How this is happening? How this is happening that where this energy is going? it appears that in beta decay, energy is not conserved. But this is not correct. Energy is always conserved. So how to solve this problem? Energy is not conserved in beta. It appears. Okay? Because beta spectrum is continuous, while we are getting the EM maximum mass difference equal to EM, only one discrete value. So where the difference EM minus E beta prime, E beta double prime is going. So it appears energy is not conserved. Number 2. Angular momentum conservation. Beta decay, I am giving only one example, you guys have done that. One beta decay say neutron is decaying to a proton plus beta particle minus charge. We know that beta minus is electron. So spin angular momentum of neutron is half h cross. Proton is also half h cross. Electron is also fermion half h cross. So angular momentum of the resultant system is half h cross, half h cross. This can combine, these vectors can combine to give you 1 by 2 plus 1 by 2 and both are parallel. 1 by 2 and 1 by 2. This becomes 1. And this they are anti-parallel means one is down and one is up. Then this is equal to 0. So resultant is 1 and 0. Here in the initial system, it is only 1/2. So in the initial system, angular momentum for neutron is only half h cross. In the final system, we can have only 1 or 0. No half h cross. Either it should be 1 when both are parallel, these two particle system, or both are anti-parallel, that means 0. It means it appears angular momentum is not conserved. Not conserved. This is question mark. Appears. But it should not be there because all these fundamental conservation law, energy mass conservation, angular momentum conservation, they should be obeyed. But here half h cross, here 1 h cross or 0. So this is not conserved. It appears. What should we do? It means that conservation of energy mass, conservation of angular momentum law is not obeyed in beta decay, but this is not possible because in all interactions, all the conservation laws are obeyed. Then another linear momentum conservation. Linear momentum conservation, what we do? We have a decay of some isotope. So this is which isotope is decay? Maybe I say example 1H3 decay. 1H3 decaying. This is a electron, and this is daughter product. That is a, so this is the direction tangent to this here. This is a 2, 1 means 2He3. When 1H3 tritium decays by beta emission, charge increases to 2 and mass remains same. So this decay, 1H3 decays to 2He3 plus beta particle. And this is the cloud chamber picture. This is the cloud chamber picture of 1H3 decay. 1 plus H3, this is 2 plus, that means plus. So this is cloud chamber picture. This momentum vector of PE, this momentum vector of P of He, helium. I make this momentum vector diagram. This momentum vector diagram. I complete this law, this parallelogram. This parallelogram of this force momentum, this and this momentum. Two momentum, the resultant momentum. The momentum of this and momentum of this is giving some resultant momentum. Initially it is zero. Finally we have this momentum. So momentum is not conserved. How it will conserve? The momentum of this, there must be, just these must be antiparallel. Means the electron and this He3, if they are going just like that momentum conserved. But if they are not going like this, momentum not conserved, because this parallelogram gives resultant momentum. Resultant momentum is R, this R, and not zero. While starting H3 is not moving to zero momentum. But we have here momentum R, so this is not zero. It means linear momentum also appears to be not conserved. What do you mean by this? Well, because R is there, so this will be conserved if there is a momentum on this side equal to R. If both are balancing, then conserved. Otherwise, this will not be conserved. So linear momentum is not conserved. This is the cloud chamber picture of H3 decay. They have similarly other cases also 2 helium-6 decay, 2 helium-6 decay, 2 3 lithium-6 and then electron. So many pictures are out there. I am giving one example, that momentum of residual system, daughter product, momentum of electron, they must be zero because here initially zero. But resultant is R. So this is not zero. So linear momentum not conserved. Energy momentum, energy mass not conserved, angular momentum not conserved, linear momentum not conserved. It appears. So conservation laws of beta decay are not obeyed. That is the problem. For many years people were in doldrum. How to explain this beta decay? Beta decay, momentum is not conserved, linear momentum not conserved, angular momentum not conserved, mass energy not conserved. So what to do? Then there was Fermi postulation of neutrino. There came Fermi hypothesis of neutrino hypothesis. So this neutrino hypothesis was given by Fermi, and Fermi developed the beta decay also. Fermi said that, well, to see the conservation of linear momentum, conservation of angular momentum, conservation of energy mass. What we should do? He assumed, it was assumed that another particle, another fermion, that is half h cross spin, is also emitted in beta decay. It was assumed that another fermion, half h cross momentum, is also emitted in beta decay. The name was given neutrino. It is a special type of particle to satisfy the non-conservation of the energy mass and angular momentum, linear momentum. Fermi assumed that a new particle called neutrino is coming out, and neutrino is a special particle, has got special properties of neutrino. What are special properties of neutrino? Some special thing is assumed that it has no rest mass. It means its rest mass is zero. mu, its symbol was neutrino, written by symbol neutrino. mu is equal to zero, no rest mass. Okay, no rest mass. Then always moving. It is never on rest. Always moving with light velocity. This was the assumptions. You can assume anything. So far it explains some result, experimental thing. So Fermi assumed that a particle also coming out in beta decay that has name neutrino, its rest mass is zero and it's moving with the light velocity. It has no charge. No charge? Okay. The charge of, so no effect of electric and magnetic field. It has no charge, so no effect of electric and magnetic field. Means neutrino cannot be affected by applying a electric field or magnetic field. So what else? Neutrino has some special property. What else? Fourth, neutrino has half h cross spin angular momentum. It is a fermion. Fermi assumed. Fermion like electron and neutron, proton. So it is also fermion, half h cross. It obeys Fermi-Dirac statistics. So it has, okay, correct special properties like that. And also, it has several light years mean free path. Mean free path means average distance between collision. It has no charge, it has no effect of mass, electric field and magnetic field. It has no mass, so no gravitational force, no electric force, no magnetic force, nothing having effect. So it means it has almost no interaction with matter. It can traverse several light years without any collision. It can move whole galaxy in no collision because it massless, speed light and no charges. So no interaction. No interaction means difficult to detect. But remember, after several years of his theoretical assumptions of neutrino, a new special particle, Rice and Cohen designed an experimental method to detect neutrino. Very interesting. They detected neutrino experimentally and they got Nobel Prize later on. Ryan and Cohen. They found the presence of neutrino at the deep side, mind side, deep inside the earth. They went for experiment there. That I can discuss sometime else. But difficult to detect. It was detected. Using reverse beta decay. Means the process by which neutrino electron and a nuclei interacting and getting parent neutrino. So inverse beta decay, inverse beta decay. So that means if we assume the neutrino, a special particle here, present in the nature, which Fermi postulated, then let us see what will happen to the conservation law. In the presence of neutrino, the beta decay process will be beta decay minus beta decay. I can write that simply neutron decaying to a proton plus beta minus plus neutrino plus q beta or energy beta or q beta or energy beta, anything you can write, no problem. Whatever you want, that's the energy of beta. This is now the equation for beta decay. So if this is the equation of beta decay, we can see the conservation of energy and mass. Well, you can see the conservation energy mass means that total, that is the beta decay, that Em is equal to E beta plus that something. That something is now, I remove this something question mark and I write here E of neutrino. In fact, this is not a neutrino, but this is in beta minus decay. It is anti-neutrino, means neutrino also has got anti. All particles have got antiparticles, proton, antiproton. Like that, because this is a particle and this is also particle. So in the particle physics, the electron number must be conserved. So electron number, you can see that the decay of a neutron, where we have proton plus beta plus neutrino. So this is two particles. These are leptons. And here also. So these two leptons, they will have lepton number, same number. Here there is no lepton. Neutron is not lepton, proton is not lepton. These are leptons, electron and neutrino. So they have, suppose, plus one lepton number. Resultant will be lepton number plus 2. Here lepton number 0. So to conserve lepton number, one should be particle and other should be antiparticle. When these are particles and antiparticles, you can say that lepton number is conserved because this is a lepton number, say plus 1, and this is antiparticle, right, like this. This will have minus 1, lepton. And this is conserved, 1 plus 1 minus 0. Here there is also 0. So that is possible. But if both are particle or both are antiparticle, lepton number will not be conserved in the particle physics. So if we write, say, proton decay to a neutron plus beta plus, then here it should be neutrino because this is antiparticle. Antiparticle of this is particle, this is antiparticle. And this is antiparticle means this is anti-neutrino. This is electron. This is now antiparticle of electron, beta positive. And this is a particle. So electron number here 0. 0 here initially. Here electron number say minus 1 and say plus 1. Particle says plus 1 and antiparticle says minus 1. So this becomes 0. 0 conserved. So to conserve the electron number, particle physics, here the emission of one particle and one antiparticle. One antiparticle and one particle. Both cannot be antiparticle, both cannot be particle. Then lepton number will not be conserved. So this has got name because beta particle is particle. So this was called anti-neutron. Just neutron bar. This is antiparticle, so this was called particle, the neutrino. So we don't have only neutrino, but we have neutrino and anti-neutrino also. I will explain later on the difference of the neutrino and the anti-neutrino. But now you can see that energy is conserved because Em is equal to E beta plus E of anti-neutrino. So whatever energy difference is taken by anti-neutrino. So the energy of beta and energy of anti-neutrino is equal to Em. That energy is now conserved. Similarly, we will have momentum conservation, angular momentum. In beta decay now we have neutron is decaying to a proton plus beta minus plus antineutrino plus energy. So this has got half H cross. This has got half H cross. This has got half H cross. And neutrino and antineutrino are also assumed to be fermion. They also have spin angular momentum half H cross. Now here resultant is half H cross. Here there are three vectors. So if two vectors can be combined, say like both are upside, then half plus half, it can be 1. Then third, this can be combined, that these are up, then this is down. So half minus half, 1 minus half is equal to half. So half is equal to half. Means 3 vector, 2 gives resultant 1, and 1 gives half down, 1 half, 1 upside. So resultant will be 1 minus half, means half. Also it is possible that 3 vectors, it is possible that they combine such that half H cross, both may have down and this may have up. Result may be half. We want earlier result was 0 and 1. These two were giving 0 and 1. But now 3 angular momentum vectors can give you half H cross, like this. 2 gives 1 and then half anti, and 2 gives 1 down, then half up. So the result is always half H cross. So now earlier what I said, it appears the angular momentum is not conserved in 2 particle system. But now 3 particle system, we have 3 vectors, half, half, half. They can give result half or yes, half, like that. 1 and half combined, anti-product. 1 minus half. So it is possible. It means angular momentum is conserved. Earlier it was angular momentum, it appears not conserved. But when we assume that third particle, neutrino and antineutrino is coming out, then angular momentum is conserved. Okay. Now we have that He3 diagram, decay, electron, and this was twice He3, and this was the electron. So P of electron and P of this, they gave resultant angular momentum R. This was 1H3. This cloud picture, cloud chamber, picture of H3 decay. Similarly, other decay also, many like helium-6 decays to lithium-6, 2 helium-6 to lithium, 3 lithium plus beta negative plus antineutrino. So resultant R is the resultant of P of electron plus P of say this He this R this. So this should be conserved. So we have now third particle, and if we assume that third particle is going to this side with R resultant, means this is the now anti-P of antineutrino. So resultant linear momentum R of electron and helium-3 is taken by antineutrino, which is going in the direction opposite to R. So cancels, this cancels, this going here, this going here. This means result is 0. And linear momentum is also conserved. So what we have? We have that Fermi's neutrino hypothesis, which was at that time a hypothetical particle, just to explain beta decay, is now reality, and it was observed in the laboratory, detected by two scientists, Rhine and Cohen. So this explains the Fermi's assumptions of a new particle neutrino, explains all the conservation laws, conservation of energy mass, conservation of angular momentum, conservation of linear momentum. Conservation of charge already explained, because neutrino has no charge. The charge is conserved. So no problem. Like that, neutrino hypothesis is explaining everything about beta decay. We will now discuss next time Fermi theory of beta decay and try to explain Sargent diagrams. So that will be my next lecture, Fermi theory of beta decay, and we will try to explain the Sargent diagram. Then we will go further, we will go to the conservation of Petty, non-conservation of Petty, etc. That experiment also I will discuss. So today I stop here. Okay. Thank you very much for listening to me.